I'll take that as a yes. Okay, so the title is actually Compositional Inference in Probabilistic Programming. I changed it at the last minute. And let's start with telling you what probabilistic programming is about. So the idea is to make the task of probabilistic modeling easy, or easier. Because as you know, one particularly difficult thing about probabilistic modeling is that you have to do inference. And inference is computationally hard. Therefore, we have developed all sorts of clever inference algorithms that help with it. But the problem is that those things are difficult to implement, they're really painful to debug, and we really don't want to have to rewrite them every time we write a new model. So the idea is to have a formal language specifying your probabilistic models, such that based on a description of this language, efficient code for inference can be automatically generated. And the reason we call it probabilistic programming is that we choose the formal language to be a programming language extended with probabilistic effects. And in particular, a goal is to separate inference from model development, because most users will not actually even know or care how to do those things. So to make a discussion more concrete, let me introduce a pure probabilistic programming system called Turing that we have been developing for a while. And essentially, it extends Julia with two effects. So one is assume for drawing random variables from a distribution. So this just says sample a value from D, put it in the current scope with the name X, and one for conditioning. So we have this statement factor, that's a factor like in a factor graph. And then there is this sugar observe, which translates to a factor with the appropriate PDF. So here is an example of a very simple linear regression model implemented in Turing. So you sample parameters from the prior, and then you observe a bunch of data points. Any questions about this? Okay, so now the question is, so obviously this is very nice for specifying models, very easy to work with, but how do we actually do inference? And as I said, we'd like to hide it from most users, but eventually someone has to write an inference algorithm. And as we know, there is no one single best algorithm that we want to apply in all cases. So why don't we design the system in such a way that it's actually easy to come up with new inference algorithms or combinations of existing ones? So let's make the task easy not only for the user, but also for a developer of the inference backend. So what I'd like to talk about today is compositionality of inference algorithms. So we know that there are certain aspects in which inference algorithms can be combined together. And ideally, we'd like our implementation to reflect that, so that if things are compositional, we can literally just put them together. And there are several different things that can mean. So for example, we may want to apply different algorithms to different parts of the model. Say I have something where I want to do Gibbs sampling or discrete variables and HMC on continuous ones. And that's something a lot of people work on, but this is not what we're going to talk about today. I'd like to focus on the other 2 points here, which is one is that we may want to apply one algorithm to the output of another. For example, I do my variational inference and I use it as a proposal in importance sampling. And another one that's a bit less intuitive is composing program interpretations that we'll get to later. So in order to be able to apply one algorithm to output of another, we need to have some sort of standardized representation so that the input and the output are in the same format. For example, if I write my sampler in such a way that it gives back just a set of samples, then I cannot really do anything else. So there are different things you could do here. For example, you could compile to a factor graph and then do operations on these factor graphs. But then what to do if my model doesn't correspond to a factor graph? So we have a very nice representation for general probability distributions, and that's a probabilistic program itself. which leads to the question of, can we write inference algorithms as program transformations? Because clearly, if we can, then they trivially compose. And what people usually mean when they say inference as program transformation is something that I'll show you. So say we have a situation like this where we draw a weight from a beta distribution and observe a value true from a Bernoulli with that weight. So those of you who know about exponential families know that this is equivalent to this, where we sample from a modified beta distribution with different parameters, and then we have a factor that corresponds to a model evidence here. Okay, so those two representations, they describe exactly the same distribution. But this one is obviously better, because if you view it as an importance sampler, this thing samples from the prior, and the weight is likelihood, while this thing samples from the posterior, and the weight is model evidence. So this is the best importance sampler we can get. And this certainly is an example of inference as program transformation. This is the kind of thing that people usually think of, for example, in compiler optimizations. You do some sort of local modification to the program where you can show that two things are equivalent, therefore you can rewrite an expression. And that's certainly true. But then there is another aspect. I think we can take this notion of inference as program transformation even further than that. For example, suppose I have the following not very interesting state space model, and I want to run SMC on that. The naive thing to do would be to take this program, apply our SMC algorithm that spits out a bunch of samples. But I can actually implement SMC as model transformation. So my SMC transforms a program to the following one. So you can actually read from it that this represents this is really an implementation of an SMC algorithm when we have a system of particles, and for each particle we perform actions separately, accumulating weights for them where the observes happen, and after each observe we resample the system of particles. So this is a straightforward implementation of SMC, but you notice that this is still a probabilistic program because we still have those assume statements here. So you could say that this is a program in Turing, not a program in Julia. And therefore, we can still do stuff with it afterwards. If I want to be really comprehensive, I can add the following lines and introduce this artificial conditioning by model evidence or the pseudo marginal likelihood at the end. And if I do that and I select one particle at random at the end according to weights, actually this program is completely equivalent to this one in terms of denoting the same probability distribution. Okay, I'm going to let that sink in. Any questions about that? Yes?
Do we have to assume that the number of particles is infinite?
No, this statement is true for any number of particles, even one. So for one particle, this doesn't do anything. It's exactly the same program. But for any number of particles, those programs are still equivalent. And if we write an inference as a transformation like this, we can actually compose them. So this is the one that I really like. There is this algorithm called particle-independent metropolis Hastings, which uses SMC as a proposal distribution for a Markov chain. And actually, PIMH can be implemented exactly as a composition of SMC with metropolis Hastings samples from a prior. So this actually works. So that's one aspect of how we can make inference compositional by doing it as a program-to-program transformation. But there is another one that I'd like to talk about, and that's composing interpretations of a probabilistic program. Because ultimately, I have a program that has some probabilistic statements in it. So say I have a Turing program. What I will want to do ultimately is to translate it to some Julia program that I will execute. Good. And for different inference algorithms, I will need different interpretations of probabilistic effects in Turing. And those interpretations are different, but they share common patterns. And it turns out that we can actually design an implementation that reflects this thing. So there is this very nice tool called monad transformers that I'd love to talk to you about, but I'm afraid that's a story for another time. So let me just briefly list some of different interpretations that we might expect so that you have an idea of the problem that we're trying to solve. So a very simple algorithm I might want to implement is importance sampler. So I sample from the prior, and I keep the likelihood as my weight. And in order to implement that, I just rewrite those probabilistic effects in the following way. So for assume, I just draw a value at random, so call my random number generator to get a value from the distribution. And for factor, I accumulate weight. And then my probabilistic program becomes a func, which is a function with no argument. And every time I call it, I get a fresh sample with a weight. I accumulate the weights, and that's a representation of my posterior. So here, it's a func that accumulates a weight. If I want to do some particle methods like SMC that we've seen about, that we've just seen, then assume is still the same. We just draw a random number. But for factor, we accumulate weight, and then we have to resample. So in order to implement that, I will represent my program as a coroutine, which is like a function, but it stops at several times before it's finished. So it goes for a while, and after each statement, it actually stops, and it returns the control to the parent that can perform resampling, and then it's restarted. So you can see that there is this pattern that we repeat those two things, but then this one is different. Again, if I want to do random DB, which is essentially a single-site metropolis Hastings, where I update one variable at a time, then my inference algorithm, so then my probabilistic program becomes a function of a dictionary. And this dictionary stores the values of my random variables from the previous run. So for assume, I want to look up the value. If it's there, then I put it in the scope. Otherwise, I draw a fresh one, and then I put it back in the database. Another one, say I want to do Hamiltonian Monte Carlo or anything else that's gradient-based. Then what I want to do is interpret my probabilistic program as a function from a dictionary of values of all my parameters to a density. So for each assume, I will compute a density of the parameter, because I assume that I already have a proposal for all the values, and I just want to compute their density. So both assume and factor will just update my density. And then I run my favorite automatic differentiation tool and get a gradient. So you can see that this is like what we've seen with weight before, but now we also have another component here. And it turns out that we can actually modularize it, different interpretations very nicely using monad transformers. So I drew a map of things that I have identified and implemented so far. Don't have time to go through all of it. But basically, the ellipses are different monad transformers, which will stand for different parts of interpretation of a program. And the rectangles are inference algorithms. And what does this say? That, for example, we have this weighted, which corresponds to accumulating a weight, as we've seen in the importance sampler. There's this empirical, which is viewing, essentially maintaining a collection of samples rather than one sample. And finally, there's particle, which says that we have a computation that stops at certain points. And if we put those three things together, we can get very easy an implementation of sequential Monte Carlo. And actually, we can also get an implementation that puts those two things together. So we compose all those interpretations, and at the end, we get a program-to-program transformation. So the ultimate composition. Okay, and there's some other stuff here as well. There's not that much of it yet. This is just things that I have implemented so far, but I think there can be potentially much more done here. So finally, if you know Haskell, you can give it a try. We have a library that composes those things using monad transformers. If you don't know Haskell, you'll have to wait until we put those things in Turing, which hopefully will happen sometime soon. Okay, thanks a lot.
Again, excellent timing. We have time for questions.
Zubin?
So just to clarify, in the diagram that you had before, the operations that you defined could apply to any probabilistic program in the language, right?
Yes.
So the object D, the distribution object D, could be itself any probabilistic program in the language.
You mean this D?
Right?
No, so this D is restricted to be a primitive distribution. So something that you can not only sample from, but also compute the density for. So those are also things like normal, gamma, and so on.
But the sort of but this first thing I said still holds in terms of like you can do PIMH on sort of as a transform on any probabilistic program.
Oh, absolutely any probabilistic program, yeah.
So what if you wanted to do more standard compiler transformations like rewriting loops or hoisting things out of loops? Would that also fit into this framework as well, the monad transformer framework, or would you need to use other methods for that?
So for that, you need essentially a compiler. You can write your compiler with monad transformers, or you may choose to do it any other way. But it wouldn't fit into this particular framework. You would probably need a separate pass over your code to do this transformation first.
So because you showed these examples of composable inference procedures, you now have potentially a huge space of possible inference procedures, right? So would it make sense to take a look at for a specific probabilistic problem that I really care about to search over the space for inference procedures which really work quite well? I mean, as almost a black box, right? Let it run overnight, and in the morning comes back and say, here's this procedure which you can run, and it will work great on your model. Is that something that's potentially achievable or useful?
Potentially, yes. At the moment, the search space is not that big. So, but as we get more and more building blocks, then that is definitely something that we'll have to worry about. But just going into the future a little bit, I think that once you get to this point, you can write your code that tries different inference algorithms as probabilistic program itself. And therefore, you should be able to, write some sort of reflexive algorithms. Let's not fantasize too much. But yes, we will search the space.
I got a question from the kind of practical aspect. How do you find debugging this code of this monad transformation in practice? Is that not hard to essentially step through those different transformations to sort of figure out what's going on?
On the contrary, it's very easy because you have different parts that each work separately. So you can unit test them if you would, rather than having a big transformation where you're not sure how things interact together. So if you arrange it well as monad transformers, then you don't have any unexpected interactions between your effects that you might otherwise get.
And so that is also the reason why you're using monads to keep the states and avoid the shared memory changes. Is that also the reasoning behind that?
Yes, in particular, modifying a state is an effect that can work in weird ways with probabilistic assignment, for example. Yep.
An alternative to designing a probabilistic program is to provide code in an existing language that samples from the distribution, which uses all the type checking, error checking of the existing language. Mm-hmm. And Julia has probably the best reflection of anything except possibly F#. Did you consider that option?
So what?
So you've used Julia's powerful macro capability to build yet another DSL on top of yet another language, and somehow it feels to me like there must be some way to write code in raw Julia, which you can type tag as probabilistic and then interpret that instead.
Yeah, so this is a very shallow embedding of a DSL in a sense that you can actually write any Julia code inside Turing. And you could probably write some sort of type system extension that would allow you to analyze the Turing code before the expansion, but we haven't tried that. We haven't had any major problems with debugging so far, so we didn't think that was necessary at this point.
Okay, can I ask a final question? When will the Turing be available?
Soon.
Soon. Okay, great. Let's thank Adam again. So we continue on the theme of probabilistic programming with Andy Gordon from Microsoft Research talking about Fabular, regression formulas as probabilistic programs.
Thanks, Sebastian. Okay, so this is indeed continuing the theme of probabilistic programming. In fact, this is partly joint with Adam, who was an intern with us here last summer, and also with colleagues at, well, various other distinguished institutions. So what's this about? It's about learning from the R community. They've got some great notations for linear regression that have been completely ignored in the probabilistic programming community, and this talk is about understanding these notations and putting them into a probabilistic programming language. So the first part of the talk, I'm going to talk about a sort of formal calculus of linear regression inspired by R. And then in the second part, I'll speak briefly about how we can embed that within our tabular language, which is where we get Fabular from, and also within Stan. So let me see. So let me start by just talking about a little bit about how to represent linear regression, sort of classic univariate linear regression inside a probabilistic programming language. And this is this syntax, in fact, is F-sharp style syntax, a language called Fun that we've used for some years as a notation for thinking about the semantics of probabilistic programming. So here I'm doing a standard linear regression where I've got an intercept alpha, I've got a slope beta, and so any actual point that we're modeling is modeled as sort of x times beta plus alpha to get to the line, and then adding a bit of noise. And if you write that down in your favorite probabilistic programming language, it looks a bit like this, where we define alpha, beta, and the precision pi of the noise by giving them uninformative priors, and then you have an array here that computes each of the y's given the x's. So I assume I've got an array of x as input, and then this syntax here, which is an F-sharp style array comprehension, is producing the output. So for every index z less than the number, the height of the array, which is in my example, it's like a set of students, so hence this is the size of the array. For every z, we calculate alpha plus the corresponding x times the slope and add in some Gaussian noise. And when I first got into probabilistic programming, I thought, this is really cool. This is all you need to do to write down a model like that. And then I realized that R has been doing something even more compact. And I went, wow, that's all. If you go and use LM or Elmer in R, you'll find if you want to do this kind of modeling, all you need to do is say y totals 1 plus x. So I was a bit gutted. It's pretty brief, isn't it? And then even worse, discovered the 1 plus, which is that the one part is defining it's saying that there's an intercept. That's optional. It's assumed if you don't say otherwise that it's always going to be there. So they've got it down to 3 symbols. So I thought, I think we ought to be able to learn from those guys to get some nicer notations. Because after all, we often want to do linear regressions in probabilistic programming. And also, linear regressions are often components of larger probabilistic models. So let's see if we can understand that notation. So that's our goal. So we want to embrace and extend R to get better languages. So now what I'm going to do is go through our notation. The full details of this are in a Popple paper that was published this January, so that's available on the web, so you can download it. And we also have an implementation that we've put up on GitHub. It's part of the Fabular system. But the first part, I'm going to talk about the calculus. So we have a grammar. So overall, So what I'm trying to do here is define a core calculus that corresponds to R's syntax for regressions. It is not precisely the same as R's syntax for regressions. And in the paper, I describe how we can go from their syntax to this language. This is like a sort of core language. It's a little bit more verbose than you would write in R. They've got some nice syntactic tricks, and I explain them in the paper. But we're not going to go through all of the details of that here. Okay, so basically the models look like that. So it's predicting y, and a regression is one of these formulas. So you can have some noise, you can add together two regressions, you can group a regression by some discrete variable, you can hide regression variables, and then this guy here is maybe the core of it, a predictor where the regression has some sort of predictor, either which is typically a scalar like we've seen 1 for the intercept, or it might be x, for a variate, and it has a coefficient alpha, and then alpha itself has a model. So we actually go beyond what you can do in R. So we want to cover the case of hierarchical linear models, as very nicely explained in Gelman and Hill's book, which I highly recommend if you've not read it, about hierarchical modeling. And there, the idea is that a regression, you can have regressions at the first order that predict actual data, and then you can have regressions at a second order that predict the coefficients that are used at the first order, and so on. So you have a sort of hierarchy of regressions. And that's what this syntax allows us, where the R in there is the model of this variable. And it itself conforms to this grammar. So you can have some levels of nesting. Though to be honest, the common case is either 1 or 2 levels of nesting. Okay, so that's the grammar. And I'm going to go and I'm going to talk you through it step by step. And I'm going to use this data set as an example, and this is a data set inspired by Gelman and Hill's book, and it's looking at school test scores, and the idea is you've got a collection of different schools, A, B, C, and D, and you've got a collection of students. Each row here is a student, and the idea is they sit a test at the start of the year, and they sit another test at the end of the year. I guess the hypothesis is that the school is going to add some value. So the kids are going to do better after the year than before. And we're trying to come up with a model that can explain this, and then maybe let us ask questions whether one school is better than another, or maybe predict how well a student would do at one school, and so forth. In the data, the X is the pre-test, the pre-year score. The Y is the post-test score, and our post-year score, and then this is the A, B, C, or D here refers to the school. And if you plot the data, it looks a bit like this, where a particular point is saying this child went to the went to, I think this is probably D. This sort of what is that? Yellow is D. And this child, started at say 48 and has come out at 53. Okay, so I'm going to come up with a number of models that use more and more of the data and for the kids. So the first one is totally trivial, but just to show you that we build up piece by piece, is we just have a single intercept. So this isn't going to fit the data very well, but it's the starting point. So we would write this. So this is a little bit verbose, but it's illustrating the core sort of regression, the core recursive coefficient syntax in the calculus. We say y regresses from a predictor 1, so that's going to give this flat line, multiplied by the parameter alpha, which is, which sits on the y-axis somewhere. And alpha itself has a regression as a model. In this case, it's just going to be a noise term. So this uninformative model. And if we translate that to our F-sharp-like syntax, you get this, that it's going to define a single parameter. Okay, so the alpha there introduces a single parameter with this as its prior. And then we're predicting y, so we have this array comprehension over all the students that for every student gives the same prediction, okay, lying on the line. Now, this is a very common pattern, so we're just going to allow this uninformative prior to be omitted. So if we say nothing, we just say v with an alpha, we're going to get that. And in fact, it's very common that you want to have a bunch of these, and in R, you're just allowed to not mention. In fact, in R, you can't give a name to the coefficient. So we want to allow that brevity. So you can just write v on its own, and you get this. So this syntax, new alpha, just hides the parameter. It makes up a sort of default name for it. Okay? So, and indeed, so that would mean that you could just write something as compact as that to get a single intercept. The next thing is noise, of course, a key ingredient of almost every model. And we just use this query here symbol for that, which expands out into something else that I won't elaborate. But when you go down to F sharp, it looks like this, that we have some sort of prior on the amount of noise, and then the noise term for every y just does a zero mean, a draw from a zero mean Gaussian with the precision given by that parameter. Okay? And so now, putting those together, we've got a plus operator on regressions that just adds together the outputs of the two regressions. So you're getting this sort of picture, and if we translate that into our underlying probabilistic language, it looks like this, where we're accumulating together the two parameters that are declared by the left part and the right part of this sum, and then the sum also gets injected into the production of the actual outputs from the model. So we're adding together the intercept together with the noise. Okay. And so you see a general pattern. What does a regression mean? Well, it means two things. We define some parameters, first of all, and then we also produce some sort of output. And in this case, the overall regression defines these two parameters and produces that output in that way. Okay? And now finally we get back to the regression we started with. We can write that as y totals 1 alpha plus x beta plus query. And we're going to get this sort of effect where we've got a slope beta, an intercept alpha, and we've got some noise added. And assembling together the semantics of these three components, you get this thing. So each of them separately declares a parameter. So you get the alpha from this part, the beta from this part, the pi from that part. And then down here in this, in the output part of the comprehension, we add together the alpha that comes from this component, the x times beta that comes from that component, and then the Gaussian noise that comes from that component. So you see it nicely assembles together, and that's the whole point of defining the language. We've got a grammar, and then the semantics of it can be defined compositionally. And here now we get back to what I wanted. That I've said we can always drop these alphas, and we adopt a convention that the plus query is sort of always present in regressions. You always add one bit of noise to every query if you haven't done otherwise. And so y totals 1 plus x will give you this. So we're sort of back to where we wanted to be. But we can go further. In that data set, you remember that we know which schools each student belongs to, and we suspect that the schools have got different performance, so I'd like to be able to measure that. One way is to say, well, there's going to be a separate intercept per school. So we've got this new operator, par_s, that has the effect of modifying a regression. So we've got a regression here that would give a single line. And by saying par_s, what we do is introduce, we duplicate the parameters on the left-hand side, one for each school. So there was an array of reals for, there was a single parameter alpha on the left, and so it becomes an array of parameters chosen by whichever school that the student belongs to. So if we translate that out, you get this model where the parameter now is defined by a comprehension. Previously, this was just a scalar, but now it's an array. So the par_s has had the effect of modifying the parameter of the underlying model by making an array of them. And then we also have to modify the output of each model. So that instead of there being a single alpha, there's one for every school. So we need to say S of Z. So that's giving us back which of the four schools corresponded to Z, and we use the coefficient belonging to it. So you get this model, and I've not shown the noise. Finally, let's just refresh our memory about the data. We'd like to model the intercepts by data that we have at the school level. Okay, so far I've only used the data at the student level, but we've got average income of parents at the school level, which we suspect may have something to do with performance of the schools. And so the way we do that is we have a hierarchical model. We have a linear regression for predicting the coefficients for A, B, C, and D. So the alphas for A, B, C, and D given the average income in each of the schools. And so we want to learn that and then use the alphas that have been learned from this process up here to define the linear regression for the actual data. And so this is an example of hierarchical regression. And this is the first time I've got an interesting regression embedded inside another. So the overall model looks like that, where the y is predicted by x, and there's only a single coefficient for x. But the baseline, the intercept for that used to predict each y, is now indexed by S as before. In the previous example, there was just an uninformative prior for the baseline, but now we're saying that the baseline is predicted by the parental income, and so we have an interesting predictor here that itself is a baseline, and it uses U to predict what the alpha is, and so you get this model here that. Well, I won't go through it in all detail, but in exactly the same way as before, we've built it up, step by step. Perfect. So, summary so far. This is the end of what I want to say about the calculus, and I'll just briefly talk about embedding within, or our use of this within probabilistic programming language, and then I'll stop. So I've explained this grammar by example. And here are all the examples I've given you. And if you run these models against the data, you see we get increasingly better fits, which is good. So this is the first formalization of these R-star formulas. And in the paper, I've got typing rules and theorems about the syntax and its semantics. And we also have proofs about how we can transform, a bit like Adam was talking about transforming probabilistic programs. We here have some. In fact, he worked on this part. We got transformations on the meaning of the regression, showing that we can actually take any hierarchical model and sort of squish it down into a less readable first-order formula. Okay, so that's the regression calculus. How do we add it to our languages? Well, Fabular is my favorite probabilistic programming language. It's an embedding of infer.net inside Excel. And the idea is you take a data set like this. This is, I think, the mammography data set from the Irvine repository, and we want to have a logistic regression of y given x1 up to x6. So if we write that in Fabular, we just do it like this. So in Tabular itself, the program looks like an annotation of the relational schema. So the relational schema is given here, where we've got columns x1 up to x6, which are these reals, and we've got a y column, which is the Booleans. And on the right-hand side here, we've written some models. So I've got a latent variable z that's given by regression. So we just add together in this syntax the 6 inputs, and then we use that to get a logistic regression to predict y. It translates down to this. So the kind of translation I showed you, in theory, in the F-sharp-like syntax, is actually implemented in Tabular. And so we get this more complicated Tabular program that would be a bit of a pain to write out by hand, but we auto-generate it from this single line. And then if you run it, it's just going to drop the inferred parameters back into the spreadsheet, and we can make predictions with it. So that's, in a nutshell, how we've embedded the regression calculus inside Tabular to get Fabular. And you can go download it and look at it, just in a nutshell. The other point is we looked at Stan. So we've done a prototype of this. There's a lot of Stan users. There's a lot of Stan models. A lot of them, in fact, are hierarchical regressions. And we went and looked at them, and we thought there's an awful lot of boilerplate that I think makes these things quite hard to understand. And so basically, it's before and after. This is our syntax where we've embedded regressions into the language, and you see we get a big reduction in size. And we did a study of about 100 models in Stan, and we found, I think, at least 80 of them would benefit from using regression formulas and would be much shorter. And so this is a sort of example. I think this is an election predictor, it's really just as a simple regression that can be written down in the syntax I've got. So it's much easier, in my view, to understand this sort of thing once you've got used to it than the more expanded version. So let me conclude there. The point of my talk was to promote this lovely syntax that R has developed over the years, to argue that it actually is a nice compositional semantics in terms of probabilities. Because I didn't really say this before, R, in fact, is not, those linear regression packages are not generally Bayesian, so they don't they don't compute probability or distributions at the end. We've shown here that it does support a probabilistic interpretation, and the benefit, one specific benefit of that is that we can have more compact probabilistic models where a lot of boilerplate that you're forced to write at the moment can be suppressed in favor of this compact syntax. So our URL is there, so go check our papers. You can download Tabular. If you want to hack on the source, it's on GitHub. So I'd welcome your comments and your contributions. Thanks for your attention.
Time for questions.
Yeah, gentleman in red.
So your motivation was partly to make the brevity of the syntax and make these things more compact. But if you overdo it, then you risk the code not being readable anymore. And you lose the boilerplate, but you also might lose things like variable names and other useful things that make it easy for teams to communicate a program, for example.
Sure.
Where do you think you are on this spectrum of Perl and Java or whatever the two streams would be in terms of readability and communication of the code?
Well, I would advocate adding this to those languages. So if it could well be someone should start off writing things by hand, but then once they get used to this sort of notation, you can then be briefer, and then you can expand it out if you want to understand, if you've forgotten what it means. I don't think the user has to choose. I think once they become fluent with this notation, I think it's preferable. But to start off with, they needn't be. They can expand it out. And I guess also, if you're saying maybe in terms of readability of someone else's model, I've shown this simple compositional translation to the core language, so it's always possible to show that. In fact, in the screenshot I showed you, I did that by, in an implementation, you write the Fabular model as a one-liner, and then there's a button you can click to expand it out, and basically it duplicates a spreadsheet or that particular sheet, but you get the full expanded version in the other sheet. So, if you're not quite sure what it's giving you, you can get it from this expanded version.
Okay, if there are no more questions, then let's thank Andy again.
Thank you.
If you can pass over the microphone. Sure. So next up, we have John Hong from the University of Cambridge, and he will reveal some secrets of matrix factorization.
Can you all hear me, or is it not? Yeah, I think it's great. Right. So I'll try to keep it under 15 minutes so that we can have coffees a bit quicker. Okay. Yep. Okay. So my name's John, and I'm currently closely working with Andrew at Microsoft. And in today's talk, I would like to briefly introduce you our recent work on matrix factorization and emphasize more on the comparison side, where we try to compare between different algorithms available in public, and also between our re-derived and novel algorithms. So just to briefly introduce you the problem, low-rank matrix factorization with missing data is a low-dimensional modeling technique where we assume that the measurement matrix, which consists of either point track coordinates or pixel intensities or some ratings in your recommender system, can be approximated by a product of two matrices. And we assume that these two matrices are of ranks which are much lower than the original measurement matrix. And such problems can arise in many computer vision and machine learning problems. But here, and also we have missing data arising from loads of problems. And the objective we're trying to minimize here is the distance between the measurement and our estimation. And the W matrix basically, sorry, is this a laser? Oh, I was pointing it the other way around. Okay, so the weight matrix basically masks out all the invisible entries, so the norm is only penalized over the visible entries. The video I'm going to show you now is on a non-rigid SFM problem, where the main cause of the missing entries is due to occlusion of this giraffe in front. So basically, we have this original giraffe sequence, and this matrix is the W matrix. Each row corresponds to each point in this video. And over time, you see that they go either black or white. So the black bits means that it's missing, and the white bits means that it's filled. So this means that, for example, this point has been, it's invisible, and then becomes visible, and then invisible, and visible again. So we have this video of this giraffe, and some parts of it is quite occluded, and 30% missing we have. And a matrix factorization algorithm at the global quotation mark minimum can produce a result something like this, where the red points describe the extrapolated points, something like this. And here we've assumed that the giraffe trajectories can be estimated by a product of two matrices, where one is the giraffe 3D points, and the other one is just a linear basis of these things. But I won't go through in detail. I'll just briefly mention why we need this global optimum. Obviously, there's no guarantee that these are global, but this data set has been run for millions of runs over the past 20 years, and this optimum value hasn't been beaten yet so far. And so we believe this is the best observed optimum for this data set. And each of these lines correspond to the points that you've seen in the video just in the previous slide. And what we see here for this data set is that the second optimum, which has only 0.6% cost above the best optimum, has a very bad extrapolation property like this. This may not always be the case for all data sets, but empirically, this is what we've observed over different computer vision data sets. So here, what we are saying is, because we believe that matrix factorization algorithms need to run over different data sets and they need to perform well, we're saying we need to reach these global optimum, or the best observed optimum for each data set. So some of the known strategies include the alternation, where you just fix one matrix and optimize over another, and vice versa until you reach some kind of convergence. Another thing which was proposed 10 years ago is joint optimization, where you just stack U and V together and optimize over both of them using just a Newton solver or a Newton-like solver. And the last approach is variable projection, which has regained attention recently. I'll just explain this briefly. What you do is you first try to minimize this cost over V only, given some value of U. And you have this V star of U because this objective is linear in both U and V. That means you can get a closed form solution for V star. And that means because this V star depends on the value of U, it's essentially a function of U, which means we can now replace this original V by this V star of U, yielding a new reduced formulation only in terms of U. Although this may look complicated because we're introducing nonlinearity, we simply need a derivative of pseudo-inverse, which is written in Magnus' book or Tom Minker's matrix notation. So why do we need all this? So what we did first was we gathered around all different algorithms in the literature over the past 10, 15 years, and we realized that there were some similarities, but because they were all written in different multitudes of different derivations, we re-derived each algorithm in a unified notation. The aim was to try and pin down exactly what the differences and similarities were between different algorithms. And we have yielded this algorithm chart, which basically, now we have a modularized blocks. So for instance, to compose this algorithm, we just need to do 1, 2, 3, and then we do step 10, and we yield another person's algorithm. This doesn't contain all the algorithms, but I ran out of the spaces, so I'm only writing some of it. So now the question is, which method works best out of all these algorithms available in public? And so the standard convention people use is they just we try and just run the algorithm on different data sets. Oh, has it? Oh, it's run out of battery, I think. I'll just try. Okay, so what we do is we try to run on different data sets and different algorithms. So the left-hand side data sets are a bit easier than the ones on the right-hand side. The ones on the right-hand side are bigger as well. And we try different algorithms over. Oh, thank you. Okay, sorry for the interruption. So we tried running different algorithms on different data sets from random starting points, meaning we draw U's and V's from just some normal distribution, and we just try and measure how many times each algorithm converges to the global or the best observed optimum for each data set. And the green means it converges 100% of the time out of 100 runs, and blue is 0. And gray means it's timed out or too slow. For instance, for these ones, it took like a day for one iteration, so I gave up on those. But they are running at the moment. So to categorize them, the first batch of the algorithms are our re-implementation / some novelties added to the original algorithms, and they are available on GitHub. And these are other of our variable projection-based algorithms available in each author's pages. And these are some other strategy-based algorithms which we've also tested. And we see that mainly the Valpro algorithms, in terms of the success rate metric, performs better than the other algorithms. And we can conclude and say, Valpro is the way forward for matrix factorization. But that's not the only problem. In practice, we also have to take into consideration of the algorithm runtime. And for instance, if we have an algorithm which, assuming constant success rate of 5%, if we have, if it only requires 10 seconds, we expect about 200 seconds for one success using geometric distribution. And for algorithm 2, which, even if it succeeds 99% of the time, if it takes 1 hour for one run, then we expect more seconds for one success on average. So somehow we would like to take into consideration of the different algorithms' runtimes. So our approach was that if we can somehow make each algorithm work 100%, well, not 100%, but as well as possible, then we can just compare the runtime of these different algorithms. So we came up with this very simple, it may sound stupid, but a thing called Rousseau, where basically we run each algorithm until we see we see two optimum twice, each of which have to be the best one we've observed so far. So not to confuse this optimum with the best known optimum for the data set, let's say the best known optimum is 1, but we observe 2 twice, we still terminate, right? So they don't always guarantee 100% convergence, but the good thing about it is it's really easy to code. And also the good thing is now the success rate for this Rousseau meta-algorithm goes all, greenier than the previous diagram. We now see more gray areas because some algorithms just have failed to observe 2 optimum twice. But then we hope that because this was limited to 100 runs, if we run more runs, then eventually, hopefully, these will all go to green. And we can do similar things, run until C in third optimum, and you can see that they go greener and, is it greener? Yeah, greener and greener. So after having achieved all, this green diagram, we believe now speed is all that matters across these different algorithms. But how can we measure this fairly? Because they all have different stages in the algorithms which can be implemented efficiently. So now we go back to this giant table of because we've modularized each step in each algorithm, we could just turn on and off different blocks and test different algorithms out. And we believe our implementation of these authors' algorithms are more accurate and faster than the previous ones because we also realized some minor tricks of getting rid of some redundant computations. So re-implement everything and they faster and more accurate. And this gives the conclusion that the Valpro, the DRW2 data sets, so these algorithms perform better than the other ones, and the DRW2 sets, which are these two, perform mildly better than the other ones. So just to summarize, our work was heavy unification of literature, and we proposed some benchmarking techniques for comparing different algorithms, and we claim that the DRW2 set is the winner across out of all these algorithms. Right. Thank you. Oh, and for any people who's doing matrix factorization, the code is available online, so you can use them.
Great. So we have plenty of time for questions. Let me start with one.
Yeah.
So most of the columns in your table were actually computer vision applications, right?
Yeah.
So are these? Do you think these findings are restricted to the particular nature of these computer vision applications, or do they also extend to, say, the statistical problems? I think net maybe means Netflix, but kind of other statistical matrix factorization problems. Do you think they would extend to that?
I think this this RTRMC, they use similar technique to VARPRO, but the reason we've categorized it here is they use a instead of computing the full Hessian, they use a conjugate gradient to solve the subproblem. But then in nature they have similarities to the original problem. So I think the techniques on how to solve these subproblems may vary, but overall these can be applied to large problems. And also you can add the regularizers as machine learning people do. The reason why we didn't include them here is because that guarantees unique solution for computer vision data sets as well. But when we tried extrapolating from those unique solutions, they turned out to be terrible, like the ones I showed in the giraffe data set. Okay. So I think they are applicable. Yeah.
So if I'm right, so a couple of your algorithms look like they're actually identical. Is that true from just the number of spots in there? So if we look at the CHLMS5 and NBRT and the last one, one before, the one before that, that's it.
Yeah.
Reference 5 and reference 2 have just the same spots, which is the last column. It does seem to have just the same spots in. Did they actually turn out to be identical?
Oh yes. So they are identical in this way. But again, as I said before, this one uses instead of computing this Hessian completely, they approximate it using, they just choose a different technique to solve that.
Rather than analysing the whole systems, could you analyse the different elements and see which elements give you a gain over other elements of the algorithm that you've got there?
Sorry, what kind of elements are we talking?
So rather than comparing algorithm to algorithm for the whole lot, could you break it down to say this element of the algorithm contributes a gain of such and such?
Oh yes, yeah, you can do that. The reason why we went for this way is because it hasn't been done before, so we thought it was time to truncate all these into different categories. But yeah, I think your comment is valid. So. The next thing is to see whether, so actually, this numbers 5 and 6, these are a particular stage of applying some kind of manifold optimization. Now we've written it in terms of this code detail, but what you can do is you can say, we've done manifold optimization, does it improve or does it not improve? That's what you're suggesting, right? Yeah, I think that's, we haven't done that, but we can do that. We can do it, yeah, in that way.
Okay. Any more questions? Otherwise, we are going off to the coffee break. But let's thank John once again more.